Hello everybody, this is Chapter 2, Lesson 5 of the Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and I'll be introducing rolling period in today's lesson. Now before we get into the equation for rolling period, we have a couple of terms to define. Over here on the left of the screen, we have T equals the natural rolling period of a vessel in seconds. The rolling period is the amount of time it takes for a vessel to go from port all the way to starboard and then back to port. Once it comes back to the same position on the port side, that is one period. B is the beam, it's a term you've seen before, in feet, and this is the total overall beam of the vessel. And then GM is something you should be very familiar with now, and that's the metacentric height in feet. Now back in World War I, there was a necessity to somehow guess or at least approximate the metacentric height of enemy vessels or vessels that were being approached on the open ocean using only variables that you knew. You either knew the length overall, the beam of ships, and some other characteristics just because of knowing different ships just like it, and you could also measure the rolling period. So this formula was developed saying that T is approximately, that's what this sign means, approximation. The rolling period is approximately 0.44 times the beam of this vessel in feet divided by the metacentric height, the square root of the metacentric height in feet. Some common rules of thumb for vessels that you'll see on the open ocean. Freighters will typically have a metacentric height about 5% of their beam. Tankers will have a metacentric height about 8% of their beam, and that extra stability is because they have free surface effect in all the tanks with the liquids they're carrying. And passenger vessels have a metacentric height that can be right around even just 2% of their beam, which is why you see very wide passenger vessels, and you also see very tall passenger vessels to give them extra reserve buoyancy to combat the possibility of a negative GM. All right, this formula is pretty simple. Let's go into a quick example problem and see just how rolling period and metacentric height are related. In this example, we have a vessel at an original loading condition of 16-second rolling period with a 50-foot beam. Now, let's say this vessel hits some rocks, it floods out one of its holds, and now its rolling period is 20 seconds. What is GM2 divided by GM1? In this, we'll find the ratio of the new metacentric height to the old metacentric height. If we get an answer that's less than 1, it means our GM2 is lower than GM1. And if we get an answer that's higher than 1, that means we actually became more stable. So in doing this, there's several different ways you can do this. You can just straight up calculate each of the GMs and then divide, or you can go this way. You know that the beam of the vessel isn't going to change. So knowing this formula, you can just rearrange and isolate B. So you have B equals rolling period times the square root of the metacentric height divided by 0.44. You know these equal 50, so you're going to have this 0.44 cancel out here. So you're going to be left with T1 times square root of GM1 equals T2 times the square root of GM2. Now if you just rearrange this, you bring your GMs to the left side and your T's over to the right side, square them both, you're going to have GM2 divided by GM1 equals your rolling period 1 divided by rolling period 2. Now keep that in mind, you have GM2 up on top, whereas your T2 is on the bottom here, and that value is squared. We plug in these values because you know this, you know your rolling periods, that's going to give you your overall ratio. And that is going to give us 0.64, which means that GM2, the new metacentric height, is only about 64% of your original metacentric height. Before we conclude the video, I just want to give you a quick little suggestion on when using this formula. If you're out on the open ocean, all vessels are subject to a certain frequency of forcing by the waves and the wind around them. In mechanical engineering and any other engineering, you learn that a mechanical system, like a spring mass damper or a spring mass system, is going to, after a certain transient period, respond exactly at the same frequency that it's being forced at. Ships are no different. If you have waves that are crashing at a certain frequency, you're going to have the ship over time at that same frequency responding at that frequency. So it's not going to be its natural rolling period. The natural rolling period is just something that if you have the ship sitting still in calm water and then you incline it over and then release it, that's the period that it's going to be responding at. So in order to negate the effects of this forced rolling, you take this formula and you do one measurement at one point, and then a couple seconds later do it again, and then a couple seconds later do it again, and have that the average of those, put that over to the side. Then maybe 3, 4, 5 minutes later, do that again, and then do it again a couple minutes later. Average all those values up, and then you should get something that's pretty close to the natural rolling period of the ship by canceling out the effects of this forced and possibly even synchronous rolling. So in this video, we talked about rolling period. We talked about an example problem on how the metacentric height and rolling period are related. And then I also gave you a quick suggestion when using this out in the field. In the next video, I'm going to talk about correcting list when you have a negative GM. Until then, I'm Lieutenant Timothy Mueller. Hope you have a great day.